Let me show you an example of a differential equation that has no solution. Consider the differential equation dy dx equals 2y over x, and let's suppose that y of 0 equals 1. I claim that this initial value problem has no solution. It's pretty easy to check because the equation is separable. In particular, 1 over y dy is 2 over x dx, and we simply integrate that. The integral on the left-hand side is ln absolute value of y, and on the right-hand side we get twice ln absolute value of x plus c. Now, we can solve for y by exponentiating. We'll move the 2 into this location, and we'll get y is a constant times x squared. But we also need to account for the initial data. And that gives us, when x is 0, y must be 1. But there is no solution to this equation at all. So we deduce that no solution exists. A natural question that arises is, how can you guarantee that a solution actually exists to an initial value problem? This is important because these differential equations model physical situations. And if you're trying to model a physical situation using an initial value problem that has no solutions, then your model is worthless. So, under what conditions can we guarantee existence of a solution? But existence is only one factor. We expect there to be only one physical outcome to a particular system or model. If there are multiple solutions to the mathematical model, how do you decide which one is the physical one? Nature should choose one. So, we want more than just existence of a solution. We would like the solution to an initial value problem to also be unique. The answer is provided by a theorem called Picard's theorem. Picard's theorem says that for the initial value problem, y prime equals f of x y, y of x naught equals y naught, meaning that the solution curve passes through the point x naught, y naught, if the function f of xy and its partial derivative with respect to y, if these are continuous, on an open rectangle containing the initial point x naught, y naught, then there will in fact exist a unique solution to the initial value problem. And the domain of definition for this solution is the interval x naught minus h to x naught plus h for some positive number h. Now, the theorem, Picard's theorem, is great because it gives us what we need, existence and uniqueness, but it's really bad because it only gives us existence and uniqueness on some small interval of definition for the solution function, and it doesn't really tell us how big that interval is. It could be some very small h indeed on which that solution arc exists. But at least we know that there will in fact exist one and only one solution arc through that initial point. As an example, consider the initial value problem. Y prime equals xy, y of 0 equals 0. In this particular instance, the function f is x times y. Now, the function x times y is a polynomial of degree 2. If you have more than one variable, you add the exponents to get the degree of a particular term. 1 plus 1 equals 2 in this case. And polynomials are continuous across their domain of definition. The domain of definition for this polynomial is the entire xy plane. So certainly on any rectangle about the point 0, 0, the origin, this will be a continuous function. If you look at the partial derivative of f with respect to y, you hold x constant in taking this derivative, and so x just comes along for the ride. The derivative of f with respect to y, you take the derivative of y with respect to y, which is 1, and multiply by the constant x. This too is a polynomial, and hence the initial point 0, 0, we can put any little open rectangle that we want around that. Our theorem, Picard's theorem, guarantees the existence of a solution curve that will go through that point. Before finding what the solution is, just looking at the initial value problem, can you tell me what the solution is? Notice if I plug the point 0, 0 in on the right-hand side, we get a slope y prime equal to 0. Could it be possible that a solution that is constantly 0 will solve this initial value problem? Certainly it satisfies the initial condition, but does it satisfy the differential equation, a function of y identically equal to 0? Well, such a function would have derivative equal to 0 everywhere. And if y is equal to 0, doesn't matter what x is, the right-hand side is going to be 0 as well. So it's easy to check y identically equal to 0 is a solution to the initial value problem. But by the Picard existence uniqueness theorem, we know that this is the only solution, the one and only solution. Let's go back and solve this, though, in a more straightforward manner. This differential equation is clearly separable, so we can separate the variables and integrate. We can separate the variables as 1 over y dy equals x dx, and then integrate. You can see that we get natural log absolute value of y equals x squared over 2 plus a constant. Exponentiating both sides, we get y is a constant times e to the x squared over 2. Now, we also have to solve the initial condition, y of 0 equals 0. But if x is 0, what solution is there to this equation? E to the 0 is just 1. 1 times c is c. We'd have to have c equal to 0. That means y is 0 times e to the x squared over 2, and that's just the function that's 0 for all x, verifying that the solution to the initial value problem is y identically equal to 0. Let's look at another example. Suppose I have dy dx equals x times the square root of y of 0 equals 0, as my initial value problem. You can also see from this particular example that y identically equal to 0 is a solution to the initial value problem. But let's go about solving this the old-fashioned way as well. On the left-hand side, we may wish to express the integrand as y to the negative 1/2. And then we get 2 y to the positive 1/2 equals x squared over 2 plus c, keeping in mind that the solution has to satisfy the initial condition y of 0 equals 0. When we plug in 0 for y and 0 for x, we get c equals 0. That gives us y to the 1/2 is x squared over 4. To simplify this, or to solve for y, we can square both sides, yielding y equals x to the 4th over 16. But wait a minute. I thought we already had a solution y identically equal to 0. But here's a second solution to the differential equation. How is it that we're not getting only one solution, we're getting 2? Let's back up and examine the original differential equation. The original initial value problem was y prime equals x, square root of y, y of 0 equals 0. The function f of xy in Picard's theorem is x times the square root of y. Now this function has problems. In particular, when y is negative, we don't get real answers. So in the xy plane, if our initial point is at 0, 0, we can only have open rectangles above the axis, but not below, because the function is not defined down here. At least it does not give real values down there. In addition, if you take a look at the partial derivative of f with respect to y, the derivative of the square root of x is 1 over 2 root x. The derivative will be x over 2 root y. Not only are we required to have y greater than or equal to 0, but y can't be equal to 0 either. This function is not continuous when y equals 0. So we have to eliminate this whole line, y equals 0. And our initial point is exactly on that line. Again, the hypotheses of Picard's theorem require that both f and the partial derivative of f with respect to y be continuous on an open rectangle containing the initial point. We see that that is not the case for this particular initial value problem, so Picard's theorem doesn't apply, and it does not guarantee uniqueness of solutions or existence. In this particular case, we found that there is one solution, and then we found a second independent solution. We found 2 solutions to the initial value problem. So existence is not the issue here, it's uniqueness that fails. Picard's theorem doesn't say anything about this particular initial value problem, though, since the hypotheses don't hold. For linear differential equations, there is another existence uniqueness theorem that is more satisfactory than Picard's theorem. So I'm going to write existence uniqueness in front of this theorem. It goes like this. For initial value problems, if P and Q are continuous on an open interval I, where x naught is inside of that interval, then there will in fact exist a unique solution to the initial value problem. There will exist a unique solution to the IVP. The The solution may exist on an interval larger than the interval I, but it will for sure exist on the entire interval I. That's better than Picard's theorem, which told us that the solution existed on some interval, but that interval could be quite small. And it gives us no indication of how to find how small that interval is or how big that interval is. In this case, we know that as long as P and Q are continuous on some open interval I, then the solution will be defined, will exist, be unique, and be defined on the entire interval I. I would now like to look at a class of differential equations called exact equations. Differential equations can sometimes be expressed in the form some function of x and y times dx plus some function of x and y times dy equals 0. Now, not all of these expressions are exact, but when they are exact, we will have a special method for solving these. In particular, I want you to suppose that we have a function z equals f of x comma y. Now, if we set that z equal to a constant, we can take the derivative of both sides. This equation defines y as a function of x implicitly. In theory, we can solve for y as a function of x by rearranging the equation. We'll take the derivative with respect to x on both sides, assuming that y is a function of x. Well, on the left-hand side, you get 0. On the right-hand side, you need to use what is called the chain rule from Calculus 3. Now, I know that Calculus 3 is not required as a prerequisite for this course. We're going to use this anyway. You're not required to know all the details of this derivation, only the method that results from it. You take the partial derivative of this function with respect to x, and then the partial derivative with respect to y, and multiply by dy dx. Rearranging this last equation, we see that 0 is df dx dx plus df dy dy. Now we can reverse all of these steps. If you start off with an equation of this form, the solution is going to be f of xy equals a constant. It will be a curve defined implicitly by some function of x and y equal to a constant c. But this method only works if the original differential equation had the first function being a partial derivative with respect to x, and the second function being a partial derivative of the same function with respect to y. If the differential equation is of the form m times dx plus n times dy, these functions aren't necessarily equal to these partial derivatives up here. How do you know when they are? In other words, how do we know that m is the partial derivative of some function with respect to x, and n is the partial derivative of some function with respect to y? Fortunately for us, there's an easy test. If m is df dx, then when we take the derivative of m with respect to y, we get the second order derivative of f with respect to y and x. On the other hand, if n is the derivative of f with respect to y, then the derivative of n with respect to x is the second order derivative of f with respect to x, and then y. There's a classic theorem that we teach in Calculus 3 called Kleros' theorem that says under nice conditions, mixed second order partials commute. these two partial derivatives must be equal under most nice situations, which means we have to have the partial derivative of m with respect to y equal to the partial derivative of n with respect to x. There is a nice notation for these partial derivatives. Instead of writing things out this way, we'll write my instead of all this. This is a standard notation in Calculus 3, so you need to know this. Also, nx will be the partial derivative of n with respect to x. The condition that has to be met if the differential equation has a nice form, easily solved by some function equal to a constant, is you must have my equal to nx. If this holds, the equation is said to be exact. If it doesn't hold, the equation is not exact. Let me put that down as a definition. The differential equation m dx plus n dy equals 0 is called exact if my equals nx. The salient point being that if m dx plus n dy equals 0 is exact, then the solution is f of xy equals some constant. Constant c will be the constant of integration, where df dx is m, df dy is n. Let me give you an example. Consider the differential equation 2xy plus the cotangent of x dx plus x squared plus the natural log of y dy is equal to 0. Is this equation exact? Well, let's check. My is the derivative of m with respect to y. Keep in mind we hold x constant for this process. So the derivative of cotangent of x with respect to y is 0. The derivative of the first term with respect to y is 2x. How about nx? Here we calculate the derivative of n with respect to x. We also get 2x. Therefore, and 3 dots in a triangular pattern like this means therefore, the equation is exact. That means we can use methods for exact equations to solve this differential equation. To solve the equation, we set f to be the integral of df dx with respect to x. And we now know that m is df dx. The integral of the first term with respect to x is x squared y. For the second term, we have to break cotangent up into cosine of x over sine of x. Since the integral is of the form f prime over f, we get x squared y plus the natural log of the absolute value of sine of x plus something constant relative to the variable that we're integrating with respect to. Constant relative to x, but that doesn't mean it's constant relative to y. What we get is an arbitrary function of y. That's a key thing that's kind of new for most of you, I'm sure. At the same time, f must be the integral of df dy with respect to y, and df dy is given by n. Well, integrating the first term is easy. When we integrate x squared with respect to y, we get x squared y. But what do we get when we integrate ln of y with respect to y? This looks like a job for, let's see, we had substitution, partial fractions, trigonometric substitutions, and integration by parts. This is a job for integration by parts. We'll set u equal to the thing that we want to differentiate. I'd much rather differentiate log of y than integrate it. We'll set dv to be everything else including the differential. If that's the case, then du is 1 over y dy, and v will be found by integrating to be y. Integration by parts works by multiplying u times v and then subtracting the integral of v du. And so we get x squared y plus uv, that's y, natural log of y, minus the integral of v du. We get y times 1 over y, which is 1, times dy. This gives us x squared y plus y, natural log of y, minus y, plus something constant relative to y, but not necessarily relative to x. What we get is an arbitrary function of x. What we found consists of two different versions of the same function f. These both must be true since the original equation is exact. Note that we have this ln absolute value sine of x, which depends only on x. It must be lurking in the arbitrary function of x here at the end. Similarly, y natural log of y minus y must be lurking in the arbitrary function of y in the first equation. To reconcile these two, we just add the first one plus the missing terms that are in here on the second one, and what is more, the solution to the differential equation was this function equal to a constant. So if we set this equal to c, what we end up with is the solution to the differential equation. By way of review, the first thing to do is to check that the differential equation is exact. If it is exact, you integrate the first term with respect to x and the second term with respect to y. You get two different versions for some function f. You reconcile those two versions, set them equal to a constant, and obtain the solution to the differential equation. Let's look at another example. Consider the differential equation 2xy plus e to the x dx plus 3y minus x squared dy equals 0. Is this exact? To test for exactness, we'll just calculate the derivative of m with respect to y, which in this case is 2x. And we'll calculate the derivative of n with respect to x. The derivative of the first term is 0 because we're holding y constant. So nx is negative 2x. Since these are not equal, we deduce that this is not exact. For now, we're going to drop this problem. If it's not exact, the methods that we're applying don't work, and so we'll move on and try a different problem. Now, another example. Suppose we have x plus y dx plus x minus y dy equals 0. Is this exact? The derivative of the first coefficient with respect to y is 1. The derivative of the second coefficient with respect to x is also 1. Those are equal. Therefore, the equation is exact, and we can solve this using the methods described earlier. Our first version of the function f will be the integral of the first term with respect to x. This gives x squared over 2 plus xy plus an arbitrary function of y. Alternatively, we integrate the second term with respect to y. This gives us xy minus y squared over 2 plus an arbitrary function of x. We have to reconcile these two versions of the little function f. You can see the x squared over 2 must be lurking in the arbitrary constant here, and the minus y squared over 2 must be lurking up here. The answer is x squared over 2 plus xy minus y squared over 2. The solution to the differential equation is that expression equal to a constant. Before moving on, do you recognize this kind of equation? This kind of quadratic equation is exactly a conic section. You might remember this from pre-calculus. But it has a mixed term, which means it's a rotated conic. There's a formula for determining what kind of conic that is. You had to calculate b squared minus 4ac to determine the kind of conic. Remember, if this is negative, the conic section is an ellipse. If it's equal to 0, it's a parabola, and if it's greater than 0, you have a hyperbola. In this particular case, b is 1, a is 1/2, and c is negative 1/2. Negative times negative is positive. The expression is positive. Therefore, these are all hyperbolas. The solution curves to the differential equation are hyperbolas. What if the differential form that you're looking at isn't exact? Is all hope lost? Well, I wouldn't be asking this question if there was nothing you could do. You can, in fact, find something called an integrating factor in many instances. We're going to suppose that my is not in x, so that the differential form is not exact. We're going to try multiplying through by some function, and hopefully if we choose this function appropriately, the differential form that results will be exact. But to be exact, mu my must equal mu in x. What are the implications for that? Using the product rule, mu m plus mu my must equal mu x n plus mu nx. This is already getting out of hand, so we'll make a specialized assumption. First, we'll suppose that mu is a function of x alone and not of y. If mu is a function of x alone, then this term will be 0. We'll have mu my equals, and if mu is a function of x alone, then this partial derivative will in fact be an ordinary derivative. Rearranging the equation, you can see that we get d mu dx times n equals, moving this term to the other side, two terms with a factor of mu. We'll have my and then minus nx. it might be possible to separate this equation. In particular, we might be able to write this as 1 over mu d mu equals my minus nx divided by n all times dx, moving the dx over, the n over, and the mu to the left. Now this is only going to work if everything here is a function of x alone. We only can integrate if my minus nx over n depends only on the variable x. If it doesn't depend only on x, then this whole method is off. So let me summarize. We get 1 over mu d mu dx equals my minus nx over n. If this right-hand side depends only on x, then the equation is separable and we can solve it. Otherwise, we might have made the assumption that mu is a function of y alone. And if we followed through on that assumption, we would have had the following: minus my minus nx over m. If the right-hand side in this case depends only on y, then the equation is separable and we can solve it. This gives us two possibilities. There are many other ways of approaching this problem, and those are explored in the homework. Let's look at an example. Suppose I have 2y squared plus 2y plus 4x squared dx plus 2xy plus x dy equals 0. Is this equation exact? To find the answer to that question, we'll calculate my, which is going to be 4y plus 2. Now let's calculate nx. That's going to be 2y plus 1. We see that the answer is no. It is not exact. But not all hope is yet lost. Transferring these equations to a new part of the light board, calculate my minus nx. If we subtract these two, we get 2y plus 1. Now, which would be better to divide by, n or m? It looks like to me that if you divide by n, you can factor the x out of the denominator. And have x times the quantity 2y plus 1. The 2y plus 1 cancels, and this expression is a function of x alone. That gives us 1 over mu d mu dx is 1 over x, and that equation is separable. To separate the variables, 1 over mu d mu is equal to 1 over x dx. Based on the symmetry alone, we deduce that mu equals x. The integrating factor that makes this equation exact is x. We're going to multiply the entire original differential form by x. What do we get? 2x y squared plus 2xy plus 4x cubed dx plus 2x squared y plus x squared dy equals 0. Just as a check on our work so far, we'll check and see if this equation is exact, and it had better be. My is going to be 4xy plus 2x. nx is going to be 4xy plus 2x. The equation is in fact exact. We solve this new equation using methods for exact equations. In particular, our function f is going to be the integral of 2xy squared plus 2xy plus 4x cubed. And that gives us x squared y squared plus x squared y plus x to the fourth plus an arbitrary function of y. On the other hand, we integrate 2x squared y plus x squared with respect to y to obtain x squared y squared plus x squared y plus an arbitrary function of x. We reconcile these two answers. These terms both appear up here. This term must be locked in this arbitrary function of x down here. It follows that the solution f equals a constant c solves the original differential form equation. I would like to talk about a class of differential equations called homogeneous equations. But let me preface the discussion of this class of differential equations by saying that we have two meanings for the word homogeneous. And we have already introduced one of those. One instance of the word homogeneous applies to linear differential equations. For linear differential equations, the equation is homogeneous if the forcing function f of x on the right-hand side is identically 0, but that's not what we mean here. So we're going to have two meanings, one word. You're going to have to interpret the meaning of that word based on the context. That's just the nature of the beast. When it comes to all terminology in mathematics, that terminology is conventional. It's based on arbitrary choices. In this particular case, there's one word, homogeneous, has two completely different meanings, and you're going to have to make that interpretation based on the particular instance. Now, in this topic, the word homogeneous applies not just to differential equations, but also to functions. So first, let me define what I mean by a homogeneous function. A function f of two variables, x and y, is called homogeneous of degree n homogeneous of degree n if, when you replace x by alpha x and y by alpha y, you get alpha to the power of n of f of x comma y. So a function is homogeneous of degree n if you can pull out factors from each of the coordinates to some power. Let me give you an example. In this example, we'll say f of x comma y is x squared plus xy. If we replace x by alpha x and y by alpha y, you can see that we get alpha x quantity squared plus alpha x times alpha y. Each term will have a factor of alpha squared. And if we factor that alpha squared out, we end up with alpha squared times the original function. This function is homogeneous of degree 2. You can see this immediately just by looking at the function. This function is a polynomial of degree 2, and every term has exactly the same degree. The first term is obviously of degree 2, but so is the second term. When a term has two different variables, say x and y, you add the exponents to determine the degree of that term. In this case, xy is a term that has degree 2. If all terms have the same degree, you'll be able to factor out alpha to that degree from the entire function. Let's consider the function f of xy equals x squared plus xy squared. From our discussion on the last example, you probably expect that this function is not homogeneous. The second term on the right-hand side has degree 3, whereas the first term has degree 2. And we can check that. If we replace x by alpha x and y by alpha y, we'll have alpha x quantity squared plus alpha x times alpha y quantity squared. That's alpha squared x squared plus alpha cubed xy squared. Try as you might, you can't factor all of the alphas out on the left. This function is not homogeneous to any degree. A differential equation is called homogeneous if it has the form y prime equals f of xy divided by g of xy, where f and g are homogeneous to the same degree. F and g are homogeneous to the same degree. This definition is very different from the definition that we gave for linear equations. These equations will not need to be linear at all and can still be homogeneous, as you shall see. There's a special method that applies to homogeneous differential equations. In particular, the method is based on setting u equal to y divided by x. If this is true, then y is x times u. If we make this substitution into the differential equation, we'll have dy dx equals f of, I'm going to write x as x times 1, and y is going to be x times u. The same is going to be true in the denominator. We'll have x times 1 and x times u. We're assuming here that both f and g are homogeneous functions having the same degree. If that's the case, we can factor x out in both the numerator and the denominator. And once you factor the x out, since these have the same degree, these will cancel. This gives us the differential equation. Dy dx, so far, is f of 1 comma u divided by g of 1 comma u. So far, we'll replace x by 1 and y by u. That's the same thing as replacing, as setting u equal to y divided by x. On the left-hand side, however, y prime can be calculated using the product rule. It's going to be x times u prime plus u. In summary, the method for homogeneous equations works like this. You start with some differential equation that has homogeneous functions to the same degree on the right-hand side. The equation is transformed into the following form. And on the right-hand side, we replace x by 1 and y by u. Why is this advantageous? Because the equation is now separable. And we can solve this equation by methods for separable equations. Once we've found u, we replace u by y over x. For example, consider the differential equation dy dx equals x squared plus y squared divided by xy. Every term in the numerator has degree 2. The numerator is a function that is homogeneous of degree 2. Similarly, the denominator is a function that is homogeneous of degree 2. The equation transforms into this after substituting 1 for x and u for y. Moving u to the right-hand side, we are now subtracting fractions. When you subtract fractions, you need a common denominator. So we need to multiply the second term by u divided by u. The u squareds are going to cancel, and that leaves us with 1 over u. With the equation now suitably transformed, we separate the variables. 1 over u du equals 1 over x dx. Again, integrating both sides, log absolute value of u equals log absolute value of x plus c. Exponentiating both sides, we get u is a constant times x. We're not done though. We're done undoing the derivative, but the original equation did not involve the variable u. U has to be replaced by what u is equal to. U is y over x. That means our solution is expressed as y over x is cx. Normally, we might solve a simple equation like this for y, but we don't need to in general. For another example, consider the equation y prime equals x squared plus y squared over xy minus x squared. According to our setup, if you set u equal to y divided by x, then we get x u prime plus u equals 1 plus u squared over u minus 1. We need to put this term over here and have x du dx equals 1 plus u squared over u minus 1 minus u. To combine these two as fractions, we need to multiply this by u minus 1 over u minus 1 and have a common denominator. Combining these, we have u minus 1 here. We'll have a minus u squared and a plus u squared that cancels out. The top will be 1 plus u. With the differential equation now transformed, it is separable. And we may write this as u minus 1 over u plus 1 du equals 1 over x dx. And then integrate. The right-hand side is trivial, log absolute value of x plus c. To create the left-hand side, well, it is a rational function, the ratio of two polynomials. And when the degrees are the same like this, the standard procedure says that the first step is long division. However, there is a way to do this without having to do too much work. And it goes like this. I wish the numerator were u plus 1 to match the bottom. But to make it u plus 1, I need to subtract 2 because it's really u minus 1. I can now break this into two integrals. The integral of 1 minus 2 divided by u plus 1. Now, that's a little slick. It is still possible to use long division of polynomials, and that you can resort to. I find this to be a little bit easier, though it takes a little getting used to. Integrating, we have u minus 2 ln absolute value of u plus 1, with the constant of integration left on the other side of the equation. With the integrations now over, you might suspect that we are now done with this problem, but we're not. The original equation had nothing to do with the letter u. We need to replace u with what it was equal to, y divided by x. Our solution is y divided by x minus 2 natural log of the absolute value of y over x plus 1 equals natural log absolute value of x plus c. There are many other forms of differential equations that we can solve by various means, but I'll leave those for the homework. Instead, I'd like to talk about a method that will give you an idea of what the solution to a differential equation looks like, even if you can't solve it. Suppose you're given an equation and you just can't figure out what method applies. There's still a way of figuring out what the solutions look like by approximating those solutions. This is going to be the simplest method, but it still has its uses. It's called Euler's method. After Leonhard Euler. Euler, and Oi, that's Euler, was the most prolific mathematician of all time. He had several hundred papers published after his death. Not only that, he was prolific in more ways than one. He had 13 children. In the last 2 years of his life, he was totally blind, and yet he continued to publish new mathematical research. He was a truly remarkable mathematician from the 18th century. Euler's method applies to initial value problems of the following form. You need to have some initial condition, some initial point that the solution curve passes through. Suppose this is the point x0, y0. We're going to first decide some distance h that we're going to go to some new point x1, and we're going to use the same distance h to get to some point x2, and so on. In other words, x sub k will be x0 plus k times h. We can figure out all these x values from the very beginning a priori. Now, if we plug the point x0, y0 into the right-hand side of the differential equation, it tells us the slope of the solution that passes through that point. Not knowing anything else about the solution, we'll follow that slope until we get to this position over here. This will give us some point x1, y1. y1 will be the point on this line passing through x0, y0, having the slope at that point. Once we get to this point, we plug this new point in and perhaps get a different slope. We follow that slope, that line, until we get to the next x. And so on, and so forth. Now that we have a picture for how Euler's method works, let's derive the method. The equation of the line passing through x0, y0 having slope f of x0, y0 is given by this. At x equals x1, y should be y1. But if I have x1 here, the difference between x1 and x0 is h, the gap between each of the x's. We can solve this for y1. y1 is y0 plus h times f of x0, y0. It follows that Euler's method in general works like this. To get to the new y, you take the old y and h times the function f evaluated at the old point. I'm going to show you how to apply Euler's method using your computers. In particular, you'll need to have some kind of spreadsheet program like Excel. We're going to apply this to the Friedman equation. The Friedman equation arises in Big Bang Cosmology, and it looks like this. dy dt squared, where y is the expansion factor for the universe, the bigger y is, the bigger the universe is equal to a divided by y minus k, where k can only take values in the set -1, 0, 1, and a is just some constant. For us, we will suppose a is equal to 1, just for sake of simplicity. With our assumption, the rate of change of the expansion factor of the universe is plus or minus the square root of 1 over y minus k. Which is it, plus or minus? As far as we can tell right now, the universe appears to be expanding, and so we will take plus. Why does the universe appear to be expanding? This was due to an observation from Edwin Hubble, among others. Back in the 1920s, Edwin Hubble, with his big 200-inch telescope, that means that's the diameter of the mirror, was able to observe galaxies far away and resolve individual stars in those galaxies. Some of those stars have a particular known brightness, and the further something is away, the more dim it gets. If you double the distance an object is away from you, it cuts the light intensity to 1/4 the original. There's an inverse square principle on light intensity. So Edwin Hubble could determine how far these stars are in these distant galaxies based upon their light intensity. Not only that, though, individual atoms within these stars emit light with certain frequencies, and you can tell which atoms are emitting those here on Earth by the frequencies that are received. Now, it turns out that if the stars are moving away from us, those frequencies should be stretched out. And that is what is observed in many cases. There are only a few galaxies which have stars where the stars appear to be moving towards us and the light is shifted to the violet end of the spectrum instead of the red end of the spectrum. In fact, Edwin Hubble was able to observe that the further away a galaxy is, the more red shifted the light appears to be. How do we interpret this? Is it true that these galaxies are moving faster and faster away from us if they're further and further away from us? Well, yes and no. A better picture is that the galaxies are like dots on a balloon. And as the balloon expands, those galaxies get further and further apart. Light rays that are transmitted between these galaxies will be more and more stretched out the longer they have to transit the distance between the two galaxies. And that's the reason why light from more distant galaxies is more red shifted. It's more stretched out. Just because the universe is expanding, just because the sign is positive. So far as we know, the universe hasn't started to collapse in on itself at this point. In fact, most recent experiments seem to indicate that the universe is growing faster and faster at a faster and faster rate. For now, we'll take the plus. According to Euler's method, the new value for the expansion factor will be the old value plus some h that we use times the square root of 1 over the expansion factor minus k. We'll also have to choose some k. We'll suppose that the expansion factor at time 0 is 0.1. And let us choose h to be 0.01. We'll choose different values a. We're going to set up a spreadsheet. First we're going to have times, then we're going to have expansion factors y, we're going to have h and k. The time is going to start at 0, and at t equals 0, y is 0.1 according to our initial data. H we chose to be 0.01. Let's choose k initially to be -1. To get to the new t's, we have to take the old t's and add the h value, which we need to convert into an absolute reference. We'll leave A2 as a relative reference. Let me show you what that does if I paste this down a little ways. Pasting this formula down, you can see how on the next line I'm still referring to the cell above, A3 now, and exactly the cell C2. The same is true on the next line, A4, the cell above. That's why this is called a relative reference, whereas this is an absolute reference referring to this particular location. According to our formula, the way to get the new value for y is to take the old value and add h, which again needs to be an absolute reference, times the square root of 1 divided by the old value minus our value for k, and that too needs to be an absolute reference. Now, I want to clear these cells, and I want to paste this down. I want to paste it down a long distance, a long ways down. How far down? Well, I'm going to have to keep going some considerable distance. So here's what I'm going to do. I'm going to press Control G, which is the go-to function. And I want to go to A, let's say 100. That should probably be enough. That puts my insertion point right here. Now I'm going to grab the scroll bar and move back up to the top. And pay attention, because this will be important when it comes time for you to work these problems in the homework. I'm going to press Shift, click, Control D. Now I've done all of these. I'm going to scroll back down to see what happened. Aha. Now, what I'd like to do is I'd like to get a plot. So I'm going to insert a chart, maybe something like this, which shows these values growing at what appears to be something closer and closer to a linear rate. It appears that the growth rate of the universe is asymptotically linear. What if we change this value k to 0 instead? How does that change the graph? It changes it just a bit, so it no longer looks like it's tending towards something linear. Let's see if we can compare these two graphs. K equals -1, which goes really, really flat, versus k equals 0, which is not quite as flat at the end. There's one more possible value for k, and that's k equals 1. And you can see that bends pretty far over. But we're going to have to go a little bit further. So I'm going to go down to A 1000. That's quite a ways down there. When I scroll back up, I need to paste some values down. Oops. Where are we at here? Shift-click, Control-D. I should have values now all the way down to cell A1000. But you can see there are problems down there. If we scroll back up and look at our graph, you'll be able to see what the problem is, or at least more about the problem. Something strange happens when the growth of the universe stops. Something happens in our data. Let's scroll down and see what happens with the data. When the y value in this case gets up to 1, we start having problems. If this number is bigger than 1, what's going on this next line? We're taking the square root. If this number is bigger than 1, then 1 divided by that is smaller than 1. And we're subtracting 1. We get a negative number under the square root. What's going wrong? What's going wrong is that we're not taking into account that when the growth of the universe levels off, it begins to decline in size, which means we shouldn't be using plus anymore. Let's see, where did those go awry again? We shouldn't be using plus anymore. We should be using minus. That fixes that one, but now we have to fix all the others. So I'll scroll down to the end, Shift-click, Control-D, and within a few seconds, we should see something going on. Let's go back up and take a gander at the graph. You can see that the graph rises to some maximum value and then drops down to 0. Not only is there going to be a big bang, there's also going to be a big crunch under this model. What happens after this? Well, after that, there are data problems still. Let's try to figure out where that happens. There. The y value went negative. If this value is negative, we have negative minus some positive number, that's negative, under the square root. Again, we get imaginary numbers in the system, and that's why we get a number error here. It doesn't make sense to try to expand this model beyond this point, where the universe comes crashing back to a point. Notice we did not solve the Friedman equation. We did not find a solution. What we did is we used Euler's method to find approximations to the values on the solution curves. And we now get an idea of what the fate of the universe is based on these approximations using Euler's method. You can see, though, even though Euler's method is a fairly crude method for approximating differential equations, it can still give you a pretty good idea about what to expect with certain mathematical models.